let's keep going. So now we're going to talk about everybody's favorite, the normal force. Now, the normal force is the force of the surface the object is acting on the object. So that's weird English. It's the force of the surface the object is on that is acting on the object. Okay, so the surface is acting on the object. Right. So the normal force is always going to be perpendicular to the surface. And without the normal force, objects would go straight through the surface. And the normal force is not always just equal to Fg. Okay? Not always just equal to Fg. And the Newton's third law pair of the normal force is the force of the object on the surface. Right. So if your mate, for example, is standing on you, then you become the surface. Right. So whatever force that guy that's standing on you is exerting on you, you are exerting that same up against him, right? And because those things are equal, that's then why you would feel the weight of him pressing on your stomach, right? So if we go and look at the normal force in these scenarios, right, here, because this block is not moving, the forces acting on it is normal going up and Fg going down. Right? So in this instance here, Fg is in fact equal to the normal force. Now, if we look in this second scenario, there's a force going that way. So now there's an Fy and an Fx, right? So if we think about the vertical line of action, right, there's still the same Fg going down, but the forces have to be equal, right? So there's a normal going up, and in this case, the normal plus the Fy is actually going to be equal to Fg. So in this case, if you're pulling kind of up on an object, the normal is actually less than Fg. And then in this instance here, you've got the Fy now going down, and the Fx is going to be going in that direction, and the Fg is same as always, the mass of the block hasn't changed. So now, in order for these forces to be balanced, we've actually got to have a normal force going up that is rather impressive, because the normal going up has to be equal to the Fg plus the Fy, which means in this instance here, the normal is actually greater than the force of gravitation, right? So if you thought that normal was just equal to Fg, then we've shown you otherwise. So now we can keep going. What if we're on an inclined plane? Now, on an inclined plane, right, we've got this issue that we've got Fg like this, but we know that we want to go find Fg perpendicular. That's going to look like this. So in order for this thing not to go through the surface, there's got to be the normal force going opposite in that direction. So in this example, the normal is equal to Fg perpendicular, right? And then for the next one, if something is falling, right, then it isn't on a surface. And if it's not on a surface, there can't be a force of the surface on the object. So in this instance, there's actually going to be no normal. How does one spell normal? There's going to be no normal for this one. And then for this one, super interesting. So let's say, for example, somebody is pressing this block against the wall with their hand, right? You can see what a gifted artist I am. Let's see what sort of forces are acting here. So there's an applied force going that way, right? But then the block's not going straight through the wall, so there must be a normal force coming this way, right? Now, interestingly here, there's still gravity acting on the block, and because the block is not sliding, there has to be some force going up that's preventing it from sliding, and that will be the frictional force. So in this instance here, not only is the normal force not the same as Fg, it's not even in the same direction as Fg, it's perpendicular to Fg. Okay, right, so now it is time for you to do exercise 3, right, which I am going to make it clear here. You have to pause and try. Okay, this one we might as well just keep rolling. Okay, ready when you are?
3, 2, 1.
Okay, I hope that didn't give you too much trouble. Let's see what's going on here. So Johnny, mass 40 kilograms, is standing on top of a crate. and the crate has a mass of 20 kilograms. So this is 40 kgs, young Johnny, and this is 20 kgs, right? And we've got to find the magnitude of the normal force acting on the crate. Okay, so in order to understand what's going on in physics, the free body diagram is our kind of like our microscope into that world that really gives us the whole picture, right? So on Johnny, there's the force of the crate on him, which is a normal force because the crate's kind of the surface he's standing on, and then there's the Fg going down, right? So that's Johnny. I'm just going to put here J. Okay, and then we've got the crate. Okay. Now, for the crate, there's going to be a normal force going up because the crate is on this surface here, and that surface is pressing up on the crate. But then the crate is still an object on planet Earth, so it's going to have Fg. But then Johnny is standing on the crate. So the action-reaction pair of this normal that the crate is exerting on the Johnny, is going to be, I'm just going to call it the force of Johnny on the crate. Okay, so for this crate, we've got these three forces in the y direction. Crate isn't moving, so the forces have to be equal, right? So the normal going up is equal to the force of Johnny on the crate going down, plus the Fg of the crate going down. Now, the force of Johnny on the crate is equal to this normal here, and because Johnny isn't moving up or down, the vertical forces are balanced. So this Fg is actually then the same as the magnitude of that normal, right? So the force of Johnny on crate is going to be the 20 times, or not 20, Johnny is 40 kilograms. So the 40 times the 9.8, which is the mass of Johnny, right? Then plus the Fg of the crate, that's now going to be the 20 times the 9.8. And let's see here. So 40 times 9.8 plus 20 times 9.8 gives us 588 newtons. And that then is going to be the normal force acting on the crate. Well done if you got that.